So in this lesson 3.6, we're going to talk about a special type of linear relationship called direct variation. And it's something that you've done before, but probably by a different name. When it comes to direct variation, you may have heard of this relationship before under the name of proportional relationships. So if you remember talking about whether linear is proportional or non-proportional, and perhaps the constant of proportionality, that's actually exactly the same topic. It's just that in Algebra 1, we kind of step up the language a little bit, and we call it direct variation. So it's still a linear equation. You're going to notice everything that we have here still graphs as a straight line. And if we solve for y, it still can be in that y equals mx plus b kind of scenario. Okay. The big part of it, though, is that the y-intercept is 0. So when we, let's define all of this first, and when we look at the equation, you're going to see what I mean. So it says two quantities x and y are said to show direct variation when y is equal to just a times x. So when your y output, when it's isolated, is equal to some constant times x, and there's nothing next to that. Okay? And so the value of a, that's what we call the constant of variation. You probably called it constant of proportionality in the middle school years. And now we're going to call it the constant of variation. And y is said to vary directly with x. So anytime you hear me say, oh, this variable varies directly with the other, you know it's going to have this type of relationship where your output is essentially just some constant times your input. Okay, so let me give you a really quick example of a situation like that. Let's pretend for a moment that I'm making... I'm making bags to sell at the football game. And every bag that I make requires 2 yards of fabric, okay? So if I say, okay, I need to make 10 bags, and I need 2 bags of fabric for each one, right? If I need to make 10 bags, then I would do 10 times 2. Oh, I'm going to end up needing 20 yards of fabric, right? If I'm only making 5 yards, 5 times 2 is 10. I would need 10 bags of, yards of fabric. If I'm only making 3 bags, I would need 6 yards of fabric. So the fact that my input, the number of bags, is always getting multiplied by 2 so I can figure out how many yards of fabric I have, and there's no y-intercept, no additional number being added or subtracted, that's what makes something like this a direct variation. It's basically your output is the product of some constant and whatever you're plugging in. Okay, so the equation y equals 2x, that's an example of direct variation, and in this particular case, the constant of variation is 2. And if you're thinking, well, that kind of looks like the slope, you would be absolutely correct. Okay, so the constant of variation is a number that your input is being multiplied by. On the graph, though, it still is the slope. So this constant of variation ends up being the slope that measures how steep your line is when you graph it. Okay, so notice that direct variation, that y equals ax, is a linear equation that is in slope-intercept form, okay, where m is the same as the constant of variation. So there is what I was just saying. The slope and the constant of variation end up really being the same in these cases. And b, well, b is always 0. That's a huge characteristic of these direct variation equations, is that b is always 0, and that means when you graph it, it's going to pass through the origin. Okay, the y-intercept is going to be 0. So you won't see that. Usually what that happens is this will just not be shown because it's just a 0, and there's your y equals mx or ax. They're synonymous, really. They're equal to each other. Okay, so it's just a special sort of subgroup of linear equations. Okay, so the graph of a direct variation equation line with the slope a will pass through the origin. Okay, It'll always pass through this origin if it is a direct variation. All right, so determine whether x and y show direct variation. If so, identify the constant of variation. So again, basically the way we're going to determine this is if when y is isolated, it has this form right here, this y equals, there it is, this y equals ax form, okay? Then we know we have a direct variation. So let's look at if we look at the first one, the big thing though is to just make sure you solve for y. So when we do this, we're going to make sure that we solve for y, okay? And then we can ask ourselves, is that equation in that y equals ax form? Okay, so that's really what we're going to be doing there. So number one, let's see, is y already isolated? It is, right? Y is by itself, everything is on the other side, and it's simplified. So the question is, does this have that y equals ax form? Okay, and it does. Here's my y, my equals, a happens to be 1/5, and then x, and there's nothing after that. So the answer here is yes. Yes, it is. When that y is by itself, this does have that direct variation equation form. And then if so, it says identify the constant. So the answer is yes, and then we could identify the constant of variation in this case as that coefficient in front of x, which happens to be that 1/5. Okay, so this one would be yes, it is. Let's try this one. Now this one does not have the y isolated, so that's going to be the very first thing I want to make sure that I do is isolate that y and reorganize it so I can see more clearly if I can put it in that y equals ax format. Okay, so I could move the 3x, but actually I think on this one it would be really smart to just move the y. Since there's 0 or nothing on this side and this is negative anyway, I'm actually going to move the y toward the right. And so that leaves me with 3x on this side. 0 plus y is still just y. And then I can maybe reorder it, right? But now that I have moved that y over and it's just by itself, even if I put it on this side, y is equal to 3x. Is that in that y equals ax form? Well, yes, it is, right? So this one is also a yes, it is direct variation. And in this case, a is, again, the coefficient connected to x. So for this one, it'll be 3. Okay. Number 3, still have to solve for y, right? We want to make sure we solve for y and then see if it's on y equals ax form. So to solve for y, I need to move the x term. At this point, I would really want you guys to be really comfortable reorganizing and solving for variables. We started doing that back in chapter 1. We've been practicing it for a while. So we're going to move the x's to the other side by doing minus 6x and minus 6x. So now I've got 4y equals, on this side I've got a negative 6x with that positive 1. And then we still have to get rid of the 4. So to get rid of a coefficient, and when we divide, we need to make sure we do it to all of the terms. We divide the entire side. Okay, and that cancels this. So now that this is in the proper format, I end up with this, and this does simplify. If I really am going to be good about it, I'm going to rewrite that as 3 over 2. So let's do that. So negative 3 over 2 if you reduce that fraction. Okay. But then really the big question is this in that y equals ax format? Well, I've got y equals a number and x, but ding, 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 this is the issue, right? It's that plus 1/4. There shouldn't be anything after this, and in this problem, there is. So the answer for this one is no. This is not direct variation. Now, it's still linear. That is still a linear function, right? It's got a y-intercept at 1/4. It goes down 3 over 2, down 3 over 2, so this is still the slope, but it doesn't fit in this category, this little sub-VIP family, right? That's the direct variation. We only, consider direct variation, those linear equations that have a y-intercept of 0, and in other words, on the equation that they don't have anything added or subtracted here on this side. So this is our deal breaker. Okay, if it doesn't look just like this or just like, this guy right here, then, and there's something added or subtracted or some other variable, then no, it's not direct variation. Okay, all right, let's go on to the back page here. Practice a couple of more. Make sure we feel good going from an equation, that's probably the most complex one, is from an equation being able to tell. So let's try number 4. Looks like y is almost alone here, but it is a negative there. I definitely need to take care of that. So we are going to divide through by a -1. Make sure you divide everything. Oops, that's supposed to be a 1. Okay. And that way, when I divide a negative by a negative, I get a positive. 15 divided by -1 is a -15. And then a negative divided by negative is a positive 2x. And if it helps, rewrite it one more time and put that x term in front of the 15 so that it looks more like our traditional y equals mx plus b equation. Okay, but then we can ask ourselves, okay, does this fit into that y equals ax mold? No, it doesn't. Once again, it's got that -15 y-intercept there. That is a deal breaker. So this one is not direct variation. Okay, let's try number 5. Number 5, I want to get y alone to make my decision. Here's y on the right side, so I've got to get rid of this 3. I'll do the opposite, which is to divide by 3. And then that leaves me with 2/3 x equals y. And if we reorganize that, it would look like this. But does that have that y equals ax form? Y equals a number times x and nothing else? Yes, it does, right? So the answer for this one is yes, that would be a direct variation, and the a value would be that 2/3 coefficient that we had in front of the x. Okay, so again, if you can get at y by itself and everything else simplified on the other side, and you end up with something that looks like this, just y equals, and then just your x term. That's all you have is the x term. You could have a coefficient connected to that, but that's the only term. There's no added or subtracted number. Then you know you have a direct variation. Okay, and then this one here, y is isolated. Everything's already, this is ready to check. Everything's already on the other side. Does this have that y equals ax form? What do you think? Yes, right? The answer is yes. And in this case, the constant of variation would be that -4 that is attached to x. So that's your direct variation. So that's how you tell from an equation whether or not an equation or a linear equation happens to be also a direct variation. Solve it for y and simplify and see if it fits that y equals ax mold. Okay. From a graph, it's actually pretty easy, right? First of all, of course, make sure it's linear, right? Most of them will be, but it's got to be linear because all direct variation are part of the linear family. They're just a smaller subgroup, okay? But remember what we talked about over here on the front. One of the big distinctions on the graph, at least, is that because that b is 0 and because there's not going to be a number added or subtracted after the x term, it always passes through the origin. So on the graph, that is hands down the easiest way to tell if what you're looking at is a direct variation, is look to see, does the graph pass through the origin and is it linear? If it can meet both of those criteria, then absolutely, okay? So let's take a look at number 7. I'm going to look at my line that I've graphed here. Here's 0, 0. Does my line pass through that point? Yes, it does, right? So here the answer for this number 7 is yes, because the graph passes through the origin. Okay, and in that case, let's find out what that constant of variation is. So remember, the constant of variation is really still the slope of the line. So if I could find, let's see, well, this is a pretty easy point here. From 0, 0 to this point, that looks like it's an increase of $10. Be careful with that. Make sure you don't just say, oh, it's 1/1. You have to think about in terms of what did the blocks representing. If it's like a word problem or if it's the context of a situation, like in this case, money over hours worked, then each of these blocks looks like it's counting by tens. So that is a $10 earning in 1 hour of work. So it's 10 over 1, or in other words, our A value is 10 for number 7. Okay. On number 8, here's the origin. Did my graph pass through that origin point? Well, no, right? It looks like the y-intercept's up here. It's coming down. It's nowhere near that origin point. So for number 8, the answer would be no. Okay, the graph does not pass through the origin, so it's not direct variation. The graph does not pass through the origin. Okay, so that's the requirement when you're looking at a graph. Okay, all right, so if you feel good about that, then let's talk about how to determine if it's going to be direct variation from a table of values, and I'm going to show you 2 different ways to do that. So it says plot the ordered pairs and then use the graph to determine whether x and y show direct variation. Okay, so we can go ahead and start plotting the points here, but I'm also going to show you, after we have graphed, a different method if you didn't have a graph in front of you, or if you just wanted an alternative way to find out if it's direct variation. You can find out from the graph without having, from the table without having to make a graph. But we're going to follow the directions here. It says plot the points. That's always good. So I notice everything is positive on my table, so I'm actually going to stick to a positive, I'm going to stick to a positive quadrant for the most part here. Okay. Maybe something like this. I can always adjust my axes so that it fits my data. So here's my y, and here's my x-axis. Okay. And then let's go ahead and plot our points. So when x is 1, y is 5. So 1, 2, 3, 4, 5. When x is 2, y is 7. 5, 6, 7. That's up here. When x is 3, y is 9. So 7, 8, 9. And when x is 4, this goes up to 11, so that's 10. That's like 11's up here. Okay, so there's the 4 points from our table. If we go ahead and graph, actually make the line, connect those points to make our line, I can see right away that this line is not going to pass through the origin. And so our origin's all the way down here, and our line is not going to make it through that, not the straight line. So the answer here is no. The graph does not pass through the origin. Okay, so no, it does not pass through the origin for this one. Okay, now let's check this one. This one's got some positive and negatives on both ends, so I'm going to center my axes much more here. So I think we're going to need all of the quadrants. We might also need to get creative so we can get all the way to that 15. So these are the things that you want to think about. Like, I'm already thinking ahead, like, oh, I got to get all the way to 15. Clearly, I don't have 15 boxes, so I might count by something different, like by 2s or 3s. So the x-axis looks like it'll be fine. So I'm going to leave those going by 1, 2, 3, 4, 2, 3, 4. That's fine. But I might have to adjust my y-axis to get all the way to 15. Maybe I'll count by 3s or something to that effect. Let's see, 1, 2, 3. Yeah, I'm going to have to go by 3. So 3, 6, 9, 12, 15. That'll allow me. That makes sense. 6, 9. Okay, so let's go ahead and graph our points and see where we land. I'm going to put -3 when x is -3, y is 15. When this is -1, x is -1, we're down here at 5 is probably about right there. And then when x is 1, we're probably right in here at about 5. And then when x is 3, we are up here at 15. Okay? And when we connect those points, let's see what happens. There's our line. Does it pass through the origin? Remember, that's the big kind of determining factor. The answer is yes, right? This one does. So it passes through the origin. Therefore, yes, this is direct variation. Okay, it shows direct variation because it passes through that origin. Okay. All right. So what I want to show you is how you in that same information without necessarily having to make a graph. So the graph is always a really nice way to tell. You can see if it passes through the origin or not. But let's say you have just a couple of tables and maybe you don't have a graph in front of you, or you don't necessarily need to make one. Here is one of the most important points here about direct variation. Let's revisit, right? Remember, so recall what we said about 10 minutes ago, that this is what direct variation looks like. Okay, y equals ax, just that. Okay, it's just y equals some x term. That's it. Well, if I go to solve for a and say, what if we wanted to get a by itself? Let's say I wanted to reorganize it and rewrite this in terms of a instead of y. Well, if I do that, I would have to divide by x on both sides, cancel that. And then I would have a new version of the same thing that says, oh yeah, you know that constant of variation? It's actually always the y to x ratio. This is huge, okay? This is what really is at the heart. I mean, yeah, we say, oh yeah, if it passes through the origin. But truly what makes these guys special and a very important subgroup of linears is the fact that that constant of variation is the y to x ratio. And because it's a constant, meaning it doesn't change, what that really means is that when we are checking for direct variation, we're looking to see, is the y to x ratio the same for every set of ordered pairs? Okay, that's a very, very nice tool to have, right? So let's test that. Let's say that we're looking at this data right here. One way to tell without graphing is to compare, and we always put the y on top, just like with slope, right? Remember, this is still essentially like slope. For this point right here, if I compare the y over x ratio, it would be a 4/3. And that's as simple as it gets. So we're going to leave it at 4/3. Then I would want to compare that to this y to x ratio. And the question is, if I compare y to x here, 8/6, does that still give me 4/3? Is it the same ratio? Well, 8/6 doesn't look the same, but we know that that does simplify. And when I simplify that and divide by 2, I do get 4/3. So these two y over x ratios are the same. Let's try this one. This y to x ratio, so I'm labeling this here, right, is 12/9. Well, 3 goes into both of those. If I simplify that, boom, it's also 4/3. 16/12. Well, 4 goes into both of those. If I divide them by 4, boom. So notice the y over x, y over x, y over x, y over x, that ratio was the same for every one of these. And so that makes this, yes, direct variation. And even better, that number that kept popping up every time, that is your a value. That y over x is your a value. So we could go now even further and say, you know what, not only is this direct variation, but this is the equation, and that's supposed to be an x, sorry. This is the equation that generated that table. It's where y is equal to 4/3 x. Whatever that y to x ratio is, that is the a coefficient. Okay, so that's one way to tell from a table without having to make the graph. You could still graph it, but it gives you that other option. Let's try this one. When we do this first ratio, that's 4/2. That's the y to x ratio. We're going to check. So that's 4/2. Well, that reduces to just 2. No problem. Okay, cool. What about this one? That would be 7/4. Well, when I change 7/4, that doesn't simplify at all. This one did, so these do not equal each other. That's already kind of a deal breaker. We'll try the next one, but I think we're pretty sold here. This one is 10/6. Well, that simplifies to 5/3, which still doesn't it does not equal the other two. So now I've gotten 2, then 7 over 2, which is like 3.5, and then 5 over 3, which is like 1 2/3. These are not a constant y to x ratio. It's still linear, guys, so be careful. This is still linear. If I did y2 minus y1, x2 minus, I would still have a constant slope, but it doesn't have that direct y to x variation. It's all different ratios when I compare y to x, and that's what makes this not be a direct variation. The y to x ratio is not constant. So the y to x ratio is not constant or the same for all of your points. Okay, and in this one it was the same. Okay, all right, flip it over then. With that concept, okay, we're going to expand on that. So we're going to talk about writing this equation. So this is just summarizing what I just talked about on the table. So solve, if we take that y equals ax and we solve the constant, or we solve for a, we'll do what we did a moment ago. Okay, if we solve this for a, we'll divide by x on both sides. It turns out that a is equal to that y over x constant. So the direct variation can be rewritten like that. It basically says, hey, that a value that's attached to x, it's always equal to the y to x ratio. Okay, so in a direct variation, the ratio of y to x is always the same. That's what we just saw on those tables. And it's the same for all non-zero data points. The only exception is, of course, the origin, because we know these pass through the origin, so that 0.00 will be in there, but all of the other points will have the same ratio, okay? All right, that becomes really handy. It allows us to be able to tell what the entire equation is of a direct variation from just one point. Okay, so the important part on this example of problems is that the ordered pair has already been given to you as being direct variation. We don't have to prove it or figure out if it is. They're telling us the ordered pair is a solution to a direct variation equation, so there's no doubt about it. They're telling us that these are part, or they're a point in a direct variation equation. So we want to identify the variation. Well, remember that constant of variation is a, and then we want to write the equation. Okay, so it says identify, that's like part 1 here is identify the constant of variation, and then part 2 is write the equation itself. Okay, so remember the equation is y equals ax. It's really easy to write the equation once you know what a is, because you just insert that number right in here and you're done. Okay, once you know what a is, you just got to put it in front of the x and you're good to go. Okay, so here's how we're going to do this. From number 1, it'd be impossible for us to write the equation for this with only one point, okay, if it were any other kind of function. But because we know it's direct variation, all I need is 1 point. Because guess what? 1 point gives me an x and a y. And we just agreed that as long as I have a coordinate, an x and y coordinate pair, I can use those, y over x as a ratio, and I can solve for a like that. Okay, so we already know a is just the y to x ratio. So when I'm given an ordered pair, all I have to do is compare the y coordinate to the x coordinate and find out what that gives us. Well, it gives us 2 over 6. You just literally put this guy on top of that one. So it gives us 2 over 6, which simplifies to 1/3. So for part 1, identify the constant of variation. Well, for part 1, here the constant of variation is 1/3. Part 2, write the equation. Not a big deal. All we're going to do is put that 1/3 right there where the a goes. So our equation would be y equals 1/3 x. That's it. This is the direct variation equation that would have given us that input-output pair. Let's try it again. So this guy right here, again, when they give you the ordered pair, they're really giving us an x and y. We already know that since this is part of direct variation, I can find my constant by just doing the ratio of y over x. Okay, so a for number 2 is 1/8, and that means that the equation for the whole thing would be just y equals that 1/8 times x, right? We just insert the a value right there in front of x, and we have the entire direct variation equation. So it's like literally taking your ordered pair and just putting this on top of that. I almost like to rotate and be like, oh, it's going to be -12 divided by -3. Boom, there it is, right? Because that's really what we're doing. We're taking the x and the y coordinate and plugging them into this formula that we know will always give us the constant of variation in a direct variation equation. So it'll be, for this one, it'll be -12 over the -3. Well, that simplifies to 4. So for part 1, the constant of variation is 4. For part 2, the equation would be y equals 4x. So I would encourage you to press pause. Go ahead and pause the video. Try these next 3 on your own independently. See if you can come up with the constant of variation as well as the equation. And then press play and see how you do. Okay? So let's go ahead and test that. So A is that y over x ratio. So in this case, A was -7, which means our direct variation equation was y equals -7 times x. How did you do on that one? Did you get it right? How about this one? A is that y over x. So that's a -4/3. So A equals -4/3, and the equation itself would be y equals -4/3 times x. For the last one, A would be -18 over -8. That simplifies to 9/4. So the constant of variation is 9/4, and the equation equals 9/4 x. Okay, so hopefully you did those independently, and now you can check, and hopefully you got those right. All you're doing is just doing the y over the x to determine a, and then inserting the a into the little formula y equals ax. All right, so let's finish out with a couple of word problems. On this next page, we have a situation where an outdoor rental center, okay, rents kayaks for a fee based on the number of hours, okay, that have been, the number of hours that you rented for. So explain why f varies directly with age. So we want to, what they're thinking, we think that f varies directly with age. Let's find out why. Well, from a table, remember we talked about this, the easiest way to tell is that if we want f to vary directly with age, it's going to be that f to h ratio, right? So if I do, let's test that. For this first one, the ratio would be 9:1, so that's 9. Let's test this one. That's 18:2, which simplifies also to 9, yeah. How about this one? 27/3. 27 divided by 3, that's also 9. Last but not least, how about this one? If I compare $36 fee to 4 hours, 36 divided by 4 is, imagine that, 9. So that y to x ratio, or in this case, I guess, f to h, but same concept, right, is the same number every time, okay? So when we explain this, because that's what they asked us to do, we can then say, well, f varies directly with age. F varies with age because the f to h ratio that we just checked all the way across here is constant, meaning it doesn't change, and so it's constant for all the values in the table. So that's how we can, confirm and justify that we're saying, hey, yes, that varies directly, because that f of h ratio is constant for all of the values in the table. Okay, write a direct variation equation that relates h and f. Well, we want f to vary directly with h, so that means f is going to equal some constant times h, And the question is, well, what's that constant? Oh, that's right. The constant is that y to x ratio that we got all the way across. So that number that kept constantly coming up every time that we did the ratio, that is your constant of variation, right? That's what we saw on the previous page. So in this case, it's just the 9. So we found, using all of these examples, that a was equal to 9, and all I have to do is insert that here, okay? So f equals 9h would be the direct variation equation that varies, or that relates to h and f. Okay, and that makes sense. Basically, however many hours you rented it for, if you multiply by 9, it gave us the fee that they're going to charge. Okay, all right. Find the total rent fee for a kayak trip that lasts 5 hours. So now they're giving us an h value. We have a function that we plug that in. So when it says find the rental fee, that means that we are looking for an f value for a trip that lasts 5 hours that have given us an h value. So we want to solve for f when h is 5, and we have an equation to do that. So f equals 9h is our equation to find the fee for 5 hours. We're just going to, oops, I didn't mean that. We're just going to plug in the 5 here. So I know that however many hours I plugged in, or I did, they're going to do times 9 to find the fee. So in this case, our fee is $45. So the total rental fee for 5 hours, is $45. So the fee for 5 hours is $45. Okay, so the fee for 5 hours is $45. All right, let's try this one. Last one. So it says here, an object that weighs 100 pounds on Earth would weigh just 6 pounds on Pluto. Assume that the weight P on Pluto, so boom, weight P varies directly, so some A value, with the weight on Earth. So the weight on Pluto varies directly with the weight on Earth. Okay, so we know it's going to be this type of relationship here. What would a boulder that weighs 45 pounds on Pluto weigh on Earth? So first of all, we got to find this constant and find out what this equation is. There's actually 2 ways. I'm going to show you 2 quick ways you could do this. So option number 1 is to use this equation. Okay, so you could use this equation, and we know that the weight on Pluto is going to vary directly with the weight on Earth. We also know that something that weighs 100 pounds on Earth weighs only 6 pounds on Pluto. So we have an ordered pair. This is Earth and this is Pluto. Okay, and so I know I can always find that constant of variation by doing that y over x, or in this case, the weight in Pluto over the weight on Earth. Okay, and so when I simplify that, I realize, oh, well, that's just, 6/100ths. There's my constant of variation. I now know that the equation for the weight on Pluto is just 6/100ths, whatever the weight on Earth is. So I used this data point, the fact that 100 pounds on Earth weigh only 6 pounds in Pluto. They gave me 2 corresponding points of data. I can use that essentially as an ordered pair, put this over that, 6 over 100, and find my constant of variation. This is exactly what we're doing on the other side of the page, and then use that constant of variation to write my equation. Okay, so we use that ordered pair, we find A, we plug in A, we have our equation ready to roll. So now if they say, what would a boulder that weighs 45 pounds on Pluto, so that's over here, if it weighs 45 pounds on Pluto, what would be its weight on Earth? So now I can plug that in here for 45 and just solve for Earth. And so to solve for Earth, we just divide by the 6/100ths. And the weight on Earth would be whatever 45 divided is by 6/100ths. It's actually 750 pounds, okay, on Earth. So if it weighs 45 pounds on Pluto, it means here on Earth it's a 750-pound boulder. That's option number 1. For direct variation, you have another option, and it's the reason why in middle school we call it proportional relationships, is because we can set up a proportion, if you like that better, and it still works. So remember, a proportion basically compares one ratio to another and says, hey, are these the same? So it compares one ratio or one data point to another. And because these are proportional, we can use that. So we would basically kind of skip the equation part of this and go straight to that data point and say, hey, if something that weighs 100 pounds on Earth only weighs 6 pounds on Pluto, then how many pounds on Earth would something that weighs 45 pounds on Pluto? Okay, so here is Earth, comma Pluto, Earth, comma Pluto. We have one data point we have all of the information for. We know that 100 pounds on Earth is equivalent to 6 pounds on Pluto, and we're going to use that piece of information to find out how much would it weigh on Earth if it's 45 pounds on Pluto. And we can set it up as a proportion. We could say, okay, what we know about direct variation is that the ratio of y is always the same. So this 6 over 100 ratio has to be the same as this 45 over e, or whatever variable you picked. And then, just as a reminder, when you set up a proportion, you can always solve these by cross multiplying, right? So we can then do cross products here and solve it that way. So we're going to do 100 times 45 is 4,500 or 4,500, and 6 times e is just 6e, and there's our equation. And then to solve for the weight on Earth, we just divide by 6. Boom. Guess what this is going to be when we divide by 6? It's going to be 750. Okay, so still the weight on Earth would, the weight on Earth would be 750 pounds. So you can either use the ordered pair to find the constant of variation and then create your direct variation equation. Once you have the equation, you can plug in whichever one you need and solve for the other one. Or you could set up a proportion, since you know the y to x ratios are always constant. That's what makes something direct variation. And you could say, well, this y to x has to be equivalent to that y to x. And then you could use cross products to solve. Both of those are going to work. As you can see, they both give us the answer. And really, I don't have a preference. As long as you show your work, you can pick the method that you like better. And that's it for direct variation. Hopefully that jogged your memory on what we used to call proportionality.